All right, so this is the pre-lab video for a pair of labs. This is Chem 106 labs V4 Microstates and E6 reaction spontaneity. And the reason I'm doing these two together is they largely talk about the same kinds of concepts. So from that standpoint, if we can kind of understand this bundle of concepts before we get into either of the labs, we'll actually be able to do both of the pre-labs pretty well, and that'll give us a pretty good jump start into the labs themselves. So what is it that we are really doing? So these two concepts, spontaneity and entropy, both come out of the chemical thermodynamics chapter, which in your textbook is chapter number 12. So what we're getting into, kind of the big broad picture in chapter 12, is the idea of a spontaneous reaction. Now, thus far, all that we've done is thermochemistry. And we've looked at kind of the reactions that occur in solution. And most of the ones that occur on their own are exothermic reactions. But what we also understand is that based on our own experiences, exothermic reactions are not always spontaneous. And endothermic reactions aren't always non-spontaneous. So just because something is spontaneous, meaning that it's happening on its own, doesn't mean necessarily that it has an enthalpy-driven kind of characteristic. There are enthalpy-driven characteristics where we have exothermic reactions that don't give us a spontaneous reaction. And then we've got the opposite occurring as well, where we've got things that are endothermic, but yet for some reason will occur on their own without any outside interference. And so to better understand the phenomenon in general, what we need to do is really get into an idea called entropy. Now, by definition, entropy is the extent of randomness in a system. Now, that particular set of words brings about some interesting kinds of concepts and thoughts, because when we think of something being random, we kind of think about it as being unplanned. But what we really mean with randomness from a chemical and physical standpoint is not uncertainty or unplanned, but rather disorganized. And the more disorganized a system is, the more ways we can distribute energy to that system and have that energy be distributed out in varying different ways. And so an alternate definition that we tend to use for entropy is the extent to which that energy that was inputted into a system can be distributed amongst the various molecules. Now, enthalpy, entropy, and free energy for that matter, which we'll talk about a little bit later, all three of those are state functions. They're all completely path independent. So everything that you learned about enthalpy in chapter 10, you're going to see again here some of the same kinds of concepts in entropy and free energy. A lot of those characteristics, a lot of those ways of calculating delta H will get applied to delta S and eventually delta G as well. Now, entropy is governed by the second law of thermodynamics. Now, remember, the first law of thermodynamics from chapter 10 is that energy could not be created or destroyed in any process. The second law applies to entropy in particular. Any irreversible process, that is one that we cannot turn back, one that is not in equilibrium, is going to result in an increase of entropy for the universe. So if a reaction is spontaneous, we will see an overall entropy increase in the universe. Now, the word universe has the same contexts and connotations in thermodynamics as it did in thermochemistry. The change in entropy for the universe is equal to the change in entropy for the system plus the change in entropy for the surroundings. And what we are saying is that in any reversible, or excuse me, any irreversible process, any spontaneous process, that entropy of the universe is going to be going up. Now, whether it's going up because of a change in entropy for the system or a change in entropy for the surroundings, that just depends. If the process is reversible, so if we have something at equilibrium where two reactions are occurring in opposite directions at the same rate at the same time, then our entropy change is equal to 0, meaning we're getting no net change in entropy, which should make sense. If we've got two equal and opposite reactions occurring at the same time at the same rate, then there wouldn't be any room for changes in entropy. But excluding those equilibrium systems, the entropy of the universe is constantly increasing. Anytime we have a spontaneous process occurring, we are going to see an increase in the entropy of the universe. Now, we often will think about things from this perspective. And from a chemical perspective, we will often look at it from the molecular scale, the molecular standpoint. And for those reasons, we have Ludwig Boltzmann to thank. Boltzmann largely is credited with describing the concept of molecular level entropy. And he does it through the context of temperature, which is, again, the measure of the average kinetic energy for the molecules in the sample, along with some other ideas that we're about to introduce. Boltzmann is kind of a low-key genius, not very well appreciated in his time. After he dies, his theories start to gain a lot more prominence and acclaim, and he becomes much more well-regarded, well-renowned after his death than during his life. But one thing that we credit Boltzmann with is this idea of something called statistical thermodynamics or statistical entropy. And it works along this kind of general concept. If we look at molecules, we know that molecules are capable of doing several different types of motion. For the most part, we have thought of molecules in one sense. When they are given energy, they move. And we call that motion, that movement, translational energy. Translational energy allows us to see an object flying through space, going back and forth, up and down, all around. That's most of what we think of when we think of internal kinetic energy. But Boltzmann said, you know what, there's actually more than one type. So when I give energy to a reaction system, or if I give energy to a substance, I'm not just going to see those molecules flying around faster. Yes, that's going to occur, but there are other ways that we can get motion that are not those. And one of those modes is vibrational energy. So if I have a chemical bond, that chemical bond, not only does it move, but it also has the capability of vibrating and stretching. And it also can spin. And so for things that are molecular, vibrational and rotational modes of motion are important. And they play a significant role in the different ways that we can maneuver and utilize that energy. So individual atoms are unable to do this. An individual atom does not vibrate. It has nothing to vibrate with. It has no bonds. And it doesn't rotate because, again, it has no axis to rotate about. But there are several different vibrational modes, different ways that that bond can stretch and maneuver. And there are different rotational modes. You know, they can rotate about the axis, they can rotate around that sigma bond. There are lots of different ways that it can go. So Boltzmann uses this idea of the fact that there's varying forms of energy and says, well, here's what I can do. Let's just take a picture, a snapshot in time. I've got a group of molecules here. I take a picture, click, click, and there in that picture are all of the different ways that those molecules are moving in that given moment. He calls this snapshot a microstate. And if he were to go and take a different snapshot at a different time, he would see a different picture of the molecules entirely. And that would be a different microstate. And so if you can imagine all of these different pictures, all of these different snapshots being taken of a molecular system at varying moments of time, what we would get was a variety of microstates. And each thermodynamic state has with it a set number of microstates. So Boltzmann's law is this: the entropy of a system is equal to the Boltzmann constant multiplied by the natural log of the number of microstates that are present. And what we can derive from this is that with more microstates, more different ways that we can picture those molecules in space, the greater the entropy is going to be. So that's Boltzmann's primary contribution. And if you go back to that picture I have of him, this is actually from his gravesite. And you can see that on his headstone, he has his equation forever emblazoned in his gravestone. Now, why did he do that? He was so convinced that he was right that he wanted to make sure that everybody knew it. And so he puts it on, he has as one of his requests that his equation be put into his gravestone, and well, as they say, the rest is history. So this would give us, the Boltzmann equation gives us a picture of what the entropy of a particular system is. So I have a set thermodynamic state, and I can measure all the different microstates, all the different orientations that go along with it. And that would give me the entropy of a given system at that particular time. Now, if I wanted to go and look at the change in entropy, then I would need to do this twice, essentially. And so delta S, the change in entropy, can be reinterpreted as the Boltzmann constant multiplied by the ratio of final microstates over initial microstates, and that ratio is natural log being taken. Overall, the kind of big takeaway here is that when we see an increase in the number of microstates in the system as we go from reactant to product, we will see an increase in entropy as well. And if we see a decrease as we go from reactant to product, we will see a decrease in entropy as well. So problems like this kind of fit into the general concept of what your Prelab is for virtual lab number 4 on microstates. So I'm going to do a pair of examples with you, and then hopefully you can kind of extrapolate from that how to solve the Prelab. And obviously, if you get stuck or in problems, feel free to reach out to me, and I'll try to give you some more guidance and information there. But let's imagine that we've got a box. And inside of that box, I've got 2 molecules. I'm going to color one of them pink and one of them blue. Now I've got 2 molecules in this box. They're separated into 2 halves. The question in front of us is how many different ways can we draw this so that they will look, I'll have different pictures each time. So I've got this box here where I've got the pink on the left and the blue on the right. Let's draw another box. And this time we will put that purple dot, that pink dot together with that blue dot. All right, and let's do it again with, I've got another box. And let's have the pink dot and the blue dot switch places. And then finally, we've got another box. And this time, the pink dot and the blue dot are on the right-hand side. And so that's it, right? Those are all four of the possible ways that we could take two molecules and separate them out in different ways in different boxes. Now let's take a look at a slightly more complicated example. Now we've got four molecules in a box separated by two halves. So if we look at it from this standpoint, this time I'm going to make it slightly easier on us. I'm going to make all the dots the same color. All the dots are going to be green this time. So 4 dots. So I could have 4 in that one, 4 in this one. I could have 1 over here and 3 over here. I could have 3 over here and 1 over here. Or I could have 2 in each. So if all the molecules are exactly the same, we would have 5 microstates. Now, if all the molecules weren't the same, let's say that we had a scenario like we did in the first example, where half of them were one color and half of them were not, were a different color. So let's say that half of our dots are green and the other half of our dots are orange. Well, in scenario number 1, in scenario number 2, we got pretty much the same idea. All 4 molecules are on one side or on the other. But now things get a little bit more complicated. Let's say I have 1 green dot on this side and 3 orange dot, or excuse me, 2 orange dots and 1 green on this side. Let's say that I have the reverse process of that. That's a different microstate. Let's say that I had different scenario now with orange dots. 1 orange over here. 2 green dots there. We need some more boxes here. I can also do the reverse of this. So an orange dot on the right-hand side, orange and green dots on the left-hand side. And then finally, I've got double dots on both sides. So I could do two green dots. Oops. Two green dots on the left, two green dots on the right, and two orange dots to match. Or the third state would be I've got an orange in each and a green in each, and there's no switching analog to that because it would be exactly the same. So what we can see here is two different concepts in play. First of all, when we increase the number of dots, just in general, more molecules, we are going to get more microstates. The other thing that we should see is that when we have more microstates, or excuse me, when we have more variety of molecules, the number of microstates is also going to increase. So this scenario had 9 microstates. Remember, our initial example only had 4, I think. And if I went to the even simpler version of it, where I only had 2 molecules in general, remember, there's really only a couple of ways to draw that one. I could have had 2 over here. I could have had 2 over here. Or I could have had 1 of each. So there were only 3 microstates here if the 2 molecules were exactly the same. If they were different, we saw that there were a couple more microstates that we could have introduced then. But the important thing to note out of all of this is that as we see greater complexity in our reaction systems, our entropy is going to increase accordingly. And so in general, we are going to see increases in entropy in these 3 scenarios. When there is an increase in temperature, as we saw in the first couple of slides, increases in temperature are going to increase the translation, the vibration, and the rotation of molecules. All 3 of those modes are going to be increased. That's going to increase temperature. Increases in volume. If I go from a small vessel to a larger one, I now have more room for those molecules to move around. They're going to have more unique ways to arrange themselves. And then finally, the number of independently moving molecules, the more molecules that I have, the more microstates, the more entropy I'm going to see. And so putting kind of all of this together, there are some key implications that we can make. We can look at entropy by phase of matter. Solids tend to have the most order and the lowest entropy. Because the molecules are very, very, very close together, they don't have a whole lot of room for translation. And so their entropies are relatively limited. Gases, because they take up the entire space of their container, because they are far apart from each other, and they tend to have the most internal kinetic energy, they are going to have the greatest disorder and the greatest entropy overall. Liquids kind of fall in the middle. They have an intermediate entropy. They have a little bit more movement and degrees of freedom in that regard, So they do have greater rotational, greater translational, greater vibrational modes than solids do, but they are confined to a general amount of space. And so they don't have a whole lot of entropy by contrast. This kind of gets us into the prelab for E6, the reaction spontaneity. What we need to do is predict the sign of entropy change for these reactions. And we're going to use that previous slide to do that for us. So in problem number 1, we are going from the liquid phase of water to the gas phase of water. Gas phase molecules tend to have more entropy than liquid phase molecules. So we would predict that there's going to be an entropy increase, which means delta S is going to be positive. In the second problem, we've got silver ions in solution and chloride ions in solution forming silver chloride solids. So think about these. These are in solution, so they are kind of like they are in a liquid. And they're going to the solid state, which has a low entropy. So I'm going from moderately disordered to very ordered. This is going to have a negative effect. We're going to see a drop in entropy, and as a result, a negative delta S. Here we have the reaction that forms iron 3 oxide. Iron metal is reacting with oxygen gas to make iron 3 oxide. The real key here is we see that even though there is solid happening here, we've got 3 gas molecules that are turning into solids. Gases have far more entropy than solids do, so we're going to see a net loss of entropy, which is going to give us a negative value. In the last one here, we've got nitrogen gas plus oxygen gas making nitrogen monoxide gas. This one's really tough to tell because in here you have 2 gas molecules being formed from 2 gas molecules. Not a whole lot of difference or notability about them. This is pretty tough to tell. So just from a pure qualitative stance, we give that one a big old question mark. Now, if we look at the standard molar entropy for nitrogen monoxide, what we would find is that it does have a positive value, and the pieces that make it, nitrogen and oxygen, actually have more combined. So the net answer here is, if you go to the molar entropy values, this is a negative value. If we had to conjecture why, we would probably go toward some things about what we saw with the microstates. 2 molecules that are different versus 2 molecules that are the same. We're going to get more microstates this way than this way. So that's probably the best, simplest explanation for why it's negative. If you saw a problem like this, though, honestly, I wouldn't blame you at all if you just kind of put up your hands and went, I don't know. Because without going to the book values here, you're going to have a hard time figuring that out. Now, along with the prelab for E6, the general concept that is going on in that particular lab concerns something called Gibbs free energy. Now, Gibbs free energy allows us to take into consideration both sides of the parameters that we've looked at thus far. Looking at things from an enthalpy standpoint in terms of, does the reaction give away heat energy or take heat energy in? And from an entropy standpoint, does the reaction gain disorder or lose disorder? Now we know which ways tend to give us reactions. We know that when enthalpy is exothermic, that tends to yield reactions that are affirmative in their spontaneity. And we know that when entropy is increasing, the entropy of the system is increasing. That tends to lead to reactions that are spontaneous as well. But there's a temperature aspect of this that also needs to be considered. There is a temperature dependence that needs to be considered. And so the overall reaction, where we take all of those into consideration, is this. This is the Gibbs free energy equation. Delta G, the change in free energy, is equal to delta H, the change in enthalpy, minus T delta S, the temperature in Kelvin, multiplied by the change in entropy. If we are at standard conditions, recall that standard conditions are near room temperature, 298 Kelvin, and one bar of pressure, or closely estimated 1 atmosphere of pressure. These are our standard conditions, and those standard conditions come with those little degree symbols that we see. So the difference between this equation and this one, not a whole lot, other than this one dictates that we have to be at these conditions. Interpreting our values of delta G. So since we've now accounted for all of those little differences, delta G actually has a really close relationship with the entropy of the universe. And so we can talk about delta G in terms of how much energy is being absorbed or released by the reaction system as it goes. And so if delta G is positive and the reaction system has to take in energy in order to go, we consider that process to be non-spontaneous. And if delta G releases energy, if it's negative, we will consider that process to be spontaneous. Now, in the event that delta G is equal to 0, that means that energy is being transferred evenly, and we have a system that is at equilibrium. Here's the chart that is really going to make a difference for E6 laboratory. This is what tells us how to interpret our enthalpy and entropy results in terms of what they do to delta G. So for example, if we have an enthalpy favored reaction where we are exothermic and the entropy is also favorable, delta G is negative. And that means that we're going to see a reaction that is always going to be spontaneous, regardless of our temperature conditions. And that should make some sense, right? The enthalpy says go. The entropy says go. Well, if neither of them are going to contradict the other, the reaction's going to go. But if the opposite is true, we have an endothermic reaction and one that does not increase in entropy, the enthalpy says no. The entropy says no. The free energy says no. Reaction doesn't go. It's going to be non-spontaneous at all temperatures. So notice, both of these occur when delta H and delta S have opposite signs. If delta H and delta S have the same sign, then what we are going to see is a measure of temperature dependence. Where what we see in delta G is going to depend on what the value of T, the Kelvin temperature, is. If we have something that is exothermic, but entropically disfavored, then what we are going to see is that this reaction is spontaneous at low temperatures. And once we get up to a high enough temperature where that entropy change is significant, it's going to flip to being non-spontaneous. And if we have something that is enthalpy disfavored, so endothermic, but entropically favored, what we'll see is that at low temperatures, the reaction will not go. But as soon as that temperature is high enough that the entropy term takes over, reaction goes. So these are important distinctions to kind of make and take here, because what they're going to ultimately allow us to do is to be pretty predictive and be able to explain why some of those anomalous kinds of reactions occur. So why do precipitation reactions occur? Precipitation reactions, we're taking something that's aqueous and turning it into a solid. That's a negative entropy kind of event. But why do they happen? Well, because the ones that do occur must have a negative enthalpy that is able to overcome the entropy and give us an overall negative. So if we've got exothermic paired with entropically disfavored, if the temperature conditions are right, we will still see a negative delta G and a spontaneous reaction. And vice versa. If I have a reaction that is endothermic, well, the reason it might occur must be because the entropy that is generated by the reaction is so much so that it is able to overcome the endothermic nature and be spontaneous anyway, especially if the temperature conditions are right. So that's it for this particular preparation. If you have any questions about either of the pre-lab activities, again, these are due on Monday, please do not hesitate to reach out to me and ask. Otherwise, I will see you in lab next week. Have a good weekend.